Welcome back to the shrine. Got a bunch of these little parts. I need to plate them in copper for selective carburization. First I need to plate them with nickel. I've been looking for some kind of power source to do the plating, and one important thing about plating any of the parts, you need to control the current, the amount of current. And so as I was looking, I came across this electroplater, and this is made by Swest. It says founded in 1923. It's electroplater, 25 amps maximum, manufactured in the USA by Swest Inc. in Dallas, Texas. 75229 is the zip code if someone's interested. 100% made in the USA. So I came across this electroplater. It was on a local marketplace, and the price was right. And so I was debating between this and buying some new switching power supply type of deal. But I went to check it out, and I ended up buying it. It's one of those deals when you meet someone in a police academy parking lot, and so I tested it. It turned on, but that's pretty much it. So upon closer examination, I found that these 6 bolts, so there's three are in, but there's a bunch of bolts missing in the back here. So someone's been inside, and the lady who sold it to me, she was in her 70s, 80s. She said she's been plating trim for cars with it, and she guaranteed that it works. And she has even included this this sticker here, so you can see Swest Inc. 1109 in North Stemmons Freeway, Dallas, Texas. And there's a phone number if I ever want to call it. And I don't know if this is a good or bad omen, but there's a couple more bolts missing on the bottom. So it had some oily, sticky something residue on it, and when I was wiping it off, it left a red blotch. So all I can think, it's, I hope it's not blood. I'm just hoping they kept it in a garage, and it was some kind of, antifreeze or maybe brake fluid. It had that sticky, oily residue. So I decided to go inside, see what's in there, especially because something rattles. Something rattles inside, and also there's one bolt here that's missing. Otherwise everything checks out. So I'm gonna go open it up, at least remove these 6 bolts that are there, and maybe do some cleaning. The bolts are completely loose. I don't know if that's a good sign or a bad sign, but I'm pretty sure someone's been inside here. So one thing that makes me really curious is I looked up how much these cost new, and that was staggering. This thing is freaking heavy. There's some material in it. So I looked it up. Here is a similar one. This one is Electroplater PM 260A, 110 volts, 30 amps. This is $378, sold by KY Hope, and $378. I mean, you can get a 30 amp power supply for $50-60. This is $380, and they say here electroplater, gold, silver, platinum plating machine, electric plater, rectifier, 110 volts, USA, blah blah blah. Here's one from eBay. As you can see, they all kind of similar. So it's got a voltage, a current gauge. It's got a knob you can adjust, on-off switch. It's got the terminals for the output. They essentially all the same. This one is $360 and $30 shipping. Grobet, gold, silver, chrome, black, chrome, nickel, electroplater, 10 volts, 25 amps. So essentially it's all the same. So the bolts are gone now. Let's look inside. So this whole back panel just comes off. There's some transformers. So there's the case, and that was the source of the rattling. You can see this is a lock washer and the nut. That's probably the ones are missing from the front dial piece. So this is model 5170. There's serial number, 120 volts, 25 amps, 397. So I'm guessing that's 1997, third month. So that would make this 26 years old, exactly to the date. Looks like there is this oily residue inside everywhere, and I think this is just some kind of brake fluid, something along those lines. There's not much on the inside. I'm not sure what I was expecting, but it's not a Baghdad battery and some grape juice. There is a transformer here. So there's a big transformer. There's a smaller transformer. So this guy down here is a bridge rectifier. You can see it's bolted to the bottom plate. So the bottom plate acts like a heatsink. The entire casement acts like a heatsink. There's some white residue here that's probably thermal paste. On the front we got the on-off switch here, so it's just a toggle switch, and then I think this is just a light that turns on, and then we have the two gauges. So this one is the voltage gauge. You can see it's got a big resistor on it. It's a shunt. And then this is the ammeter. They all seem to have copper hardware here. And then that thing is just a dimmer switch. It's the same dimmer switch that you would have in the wall. And then these are essentially the outputs. These are the outputs, and this is a fuse. So we basically got the voltage coming in here. The green wire is grounded. Then the white wire goes to the light bulb, and then the black wire is terminated in a switch. So once the switch is on, that will provide, the switch is going to provide voltage to the dimmer, and then from the dimmer we're going to have voltage going in a transformer here to the primary, and then from the secondary, you can see these two wires here from the secondary are going to the rectifier bridge, and then from the rectifier we got this secondary transformer here. So the DC voltage from the rectifier goes to this transformer, and then after the transformer it goes to the fuse, and then from the fuse it goes to the ammeter, so it's connected in series, and then from the ammeter it goes to the output, and then the other output here, the negative, is coming directly from the bridge. It's not much. I'm not sure why it costs $360. Obviously these are made in low volumes in the United States, but I don't see, you know, $360 there. I mean, if you look at part cost, these are all old school analog meters, so you're looking at 10-15 bucks each. So let's say those are 30. The dimmer switch is probably another 15 bucks. We got a big transformer here. You know, similar transformers, you can find them in battery chargers. So I think this would be the big cost item, so that would probably be 30 bucks. So we are looking at, you know, 100 bucks worth of hardware plus the housing. Somebody has to make the housing, but this can be just laser cut and then bent and powder coated. So I can see maybe $150 worth. Probably if I make, you know, 100 of these in a year, I can bring the cost down to $100, but not $350. So someone's making a lot of money with this. So if you want to get into this business, here's your chance. You saw it's pretty simple on the inside. There's this residue inside. I think it's just some kind of, you know, car engine fluid. So you might think what this thing is doing here, because we have the transformer here, and the transformer is you know, basically taking the 120 and bringing it down to whatever voltage. Actually, it's taking the voltage that this dimmer switch is providing, and then it brings it down, and then the rectifier rectifies it. Oh. If we do a close examination on this component here, you can see it's not really a transformer, because it doesn't have primary and secondary coils. All it has are just two coils. So one wire is going in, one wire is going out, and then it most likely has some kind of wire in it, and then it's got a ferrite core. So it looks like a transformer, it smells like a transformer, but it's not a transformer. What it is, it's an inductor. It's basically a choke. And what it does, you know, it resists the rise of current. So let's say that this thing is plugged in, and then you suddenly put a load on it. So you have these alligator clips, right? They are plugged in. Looks like this been through a couple world wars. So that one is rusted out, and it's like 6 foot long, and there's some probes and stuff. So anyways, you got this plugged in, and suddenly, you know, you submerge it into the water, so the current wants to rise, and if you don't have something resisting that, this can blow the fuse, because by default this thing is 120 volts and 25 amps. So you already have to run this from a 25 amp circuit. So if you don't have a choke here that would resist that current flow, then it can trip the breaker. And so that's what this inductor is doing. It's acting as a choke, and it is resisting that huge inrush current. I'd say we plug it in and see if it works at all. All I need to do, just hold it steady somehow. So you, my favorite viewer, can see the dials, because the dials are mounted at 60-degree angle. So the first task is to plug it in. Okay, that didn't blow the fuse, so let's turn it on. Light is on, and then when I turn this, you can see the voltage goes up, and the dimmer switch works, and it's buzzing, and the voltage goes up to 13 volts. Let's pull out the meter and see if it really 15 volts or whatever volts it is. A little crusty. There's green patina on all the wires, so this has definitely been used. Okay, so that is my calibrated fluke. So I'm gonna go to 5 volts and the fluke shows something, 4.8 volts. I'm gonna go to 10 volts and is at 9.9 volts. So this thing is accurate. Now we need to test it under load. So let me get a load. Put a 1 ohm resistor across the terminals. So let's see what happens. I hooked it up to a thermocouple. Make sure it doesn't blow up. It's a 10 watt resistor, so it should be good, but I put the thermocouple on it. If it's about to turn to dust or smoke, I can see it there. So let's go and turn it on. And then this dimmer is kind of janky. See, I'm turning it, so there's 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Okay, so I need to go, 90 degrees plus to turn it on. So running about 3 volts, and because it's a 1 ohm resistance, it's about 3 amps. And then this one shows about 2.5 volts. I trust the fluke. So let's go to 5 volts. You can see it's working because we got current flowing. So we got 5 volts and we got 5 amps current flowing. And the resistor is cool as a cucumber. It's at 90. It's at 20 degrees Celsius. So let's go up to 10 volts. You can hear the buzz. So 10 volts, 10 amps. This one shows 8 volts. And you can see the smoke coming from the resistor. It's funny, the thermocouple is not picking that up through the ceramic. So I'm just gonna go back. Uh-oh. That resistor smells bad. I put the thermocouple on a ceramic. The ceramic is a good insulator. So now we know 10 amps is gonna cook that because it's 10 watts. Thing is working. I got the oscilloscope hooked up to it. Let's see if I turn the lights off. Oh, it's a better picture. So let's turn this on. And then I got the 1 ohm resistor, and then let's send in some current. So there you go, 3 amps, about 3 volts, 3 volts, 3 amps, 1 ohm, and you can see the signal. It's not really beautiful. You remember inside the box there is no capacitor, so the capacitor would resist the change of voltage, so it would smooth this out, the signal. So right now the Rigol is on 1 volt, and so this would be 1, 2, 3, 4, 5 volts. So from this edge to the peak is 5 volts. That's how much the voltage is changing, and that's the dirty voltage coming out from this box and going to, plate whatever you're plating. So you can see that this voltmeter is absolutely stable, but this guy here, see, it shows the same frequency, 117 Hertz. It's double the frequency that we have in the outlet. We are in the United States and we got 60 hertz in the outlet, so this is about double of that. That's not a flat line. Again, it's 5 volts from peak to peak. These are my low nickel electrodes. They are connected to copper. The copper is not submerged in vinegar. So, there's one electrode. So I just took the strips and made it into this shape to maximize the area. Forgot to add the salt. There's gonna be no conduction without the salt. So this is 30% vinegar basically. So you got water and vinegar, there's salt in it, and then we added the electrodes. Let's turn it on again. Let's go to 5 volts. The ammeter is not doing anything, so I'm just gonna go up until the ammeter goes to like 1 amp. So I'm at full voltage, 13 volts. Yeah, I can see bubbles forming, so it's definitely working. You can see bubbles are forming on the negative electrode, so that's good. We're just gonna let it sit for a couple hours and then see how our nickel acetate looks after that. Should have a nice turquoise hue. And give it a little chance that you guys are going to see the difference between these two. But this is the bare steel and this is the one that was nickel plated. So this is the first nickel plated part. You can see that it has a different sheen. So here's the steel and the nickel plated side by side. Next thing is to copper plate. I'm going to copper plate both of them, both the one that has the nickel coating and the raw steel, and then I'm going to do some tests to see which one sticks better. You're not supposed to copper plate directly to steel because the electrochemical potential, but I'm still going to try it. I'm just curious at this point. It's my first ever copper plating. It was 10 minutes at 1.5 volts and 1 amp. So these are the results. This was the first one. It's got the boo-boo here. You can see the double cut, the little apprentice mark that I included. So this was the one that was nickel plated, and I was trying to, push this copper off, but it's not really coming off. Here's some Scotch Brite, and I'm trying, but you can see the copper is sticking to the surface. So there are some areas here probably where it wasn't cleaned properly. I just dipped it in acetone, but otherwise the plating looks acceptable, except down here in the bottom you can see this one had a hole, so when I submerged it, it probably created an air pocket and then the solution didn't get in there. But you can see this is the one that was nickel plated early. And then this guy here, this is just steel, and so when I plated it, you can see the copper is just flaking off. See that? The copper is just flaking off. Both of these were submerged in acetone earlier, but you see that? See how the copper comes off in one big sheet? So that's why you cannot plate the copper directly on steel, it will be deposited, but it will not stick to the surface. See how that is coming off? There's chemistry involved, you know, there's thousands of pages online where you can read about this. I don't want to go there. I just wanted to show you that that's what happens. So the copper comes off in these thin flakes. So here's the nickel plated again. You see, I'm scraping it off, but this was just 10 minutes in the solution. So some of the copper comes off, but underneath the nickel is holding on. You can see the copper is not coming off in sheets. Also, when I put this in a solution, the electroplater wasn't turned on, so there was no current flowing. So the electroplater is working, and that was the topic of today's video. It performed well. I need to label these jars before I forget. Hope you guys enjoyed the video. This will be a wrap. Please leave a comment, and if you're not subscribed, please do so. See you on the next one. Bye.